All right, let's dive straight in. Today, we are going deep, really deep, into the absolute core of your computer, the CPU, the central processing unit.
Yeah, and the source material we're looking at today, it really gives us a fantastic view. Not just, the parts list, but how they actually work together, that step-by-step process for handling instructions.
Exactly. So our mission here is to unpack those key components, understand that fundamental cycle, the one the processor repeats, what, billions of times a second,
Billions, yeah.
to run basically everything you do. We want to get a look at that essential engine inside your machine.
Okay, so the sources break the CPU down, right, into several critical parts. Each one has its job. You've got the control unit, the buses, the arithmetic-logic unit, the ALU, and then these special little memory spots called registers.
Let's start with the control unit. It sounds pretty central. What's its role exactly?
Well, think of it like the conductor of an orchestra. That's a good analogy from the source. Its main job is coordinating everything else, all the other bits inside the processor and even outside sometimes.
How does it coordinate?
It sends out control signals, tells everything else what to do, when to do it, and it uses these things called buses to send those signals.
Okay, buses. You mentioned those. What are they?
Yeah.
Like physically?
Yeah, picture them as internal highways. There's sets of tiny wires or connectors, really. They just transfer signals, data, addresses between all the different components.
And the sources, they come in different sizes, like 8, 16 line.
Exactly. 8, 16, 32, 64 lines wide. That width determines how much information can travel across at the same time. More lines, more data throughput.
And the main system bus,
Mhm.
it's not just one thing.
Right, good point. The system bus, which is kind of the main highway connecting the CPU to memory and other major parts, it actually has three parts itself.
3.
Yeah, there's a control bus for those signals from the control unit we talked about. An
Okay.
address bus, which says where in memory to get data from or put data to.
Makes sense.
And then the data bus, which carries the actual information, the data itself. The sources even list examples of control signals like memory read, memory write, bus request, and the clock signal, which is crucial for timing everything.
Got it. So the control unit is the manager, using buses for communication. But where does the actual thinking, the problem solving happen? That's the ALU.
That's the ALU, yeah, the arithmetic-logic unit. This is where the math gets done. Your basic add, subtract, multiply, divide,
Yeah.
but also logic operations, like comparing things is this bigger than that, or doing A and D, or not operations, even shifting bits, moving the ones and zeros around within a number. It's the real computational engine.
Okay, so the ALU crunches the numbers. But the results, or the data it needs to crunch,
Yeah.
have to be stored somewhere close by, right?
Yeah.
For speed. Is that registers?
Absolutely. That's exactly what registers are for. They are tiny amounts of memory, but they're located directly on the CPU chip itself.
Right there.
Right there. So accessing them is incredibly fast, way faster than going out to the main system memory, which the source calls, well, slow memory by comparison.
So it's like a super fast scratch pad.
Perfect analogy. It keeps the data the CPU is actively working on right at its fingertips, ready for the next immediate step. Huge for performance.
And the source specifically mentions one called the accumulator.
Yes, the accumulator is often highlighted. It's kind of a default general purpose register. It's used to hold the results of the ALU's calculations temporarily.
Okay.
But beyond that, the sources list several other really important registers, dedicated ones. They each have a very specific job in making the whole instruction process work.
Ah, okay. What are those?
Well, there's the program counter, or PC.
Yeah.
Its job is just to hold the memory address of the next instruction that the CPU needs to fetch, always looking ahead.
Next instructions address. Got it.
Then the current instruction register, the CIR. This holds the instruction that's currently being worked on. Once it's here, the control unit can decode it.
The one happening right now.
Exactly. Then there's the memory address register, MAR. This holds the specific memory address that the CPU wants to read from or write to.
Like pointing to a spot in the main memory.
Precisely. And linked to that is the memory data register, MDR. It's like a temporary waiting room for data that's either just arrived from memory or is about to be sent to memory. It bridges the CPU and the slower main RAM.
Okay. PC, CIR, MIR, MDR, and the accumulator for results. That's quite a few moving parts just for storage.
They're all vital cogs in the machine.
All right, so we have the control unit managing, the ALU calculating, buses moving stuff, and registers holding things temporarily. How do they all work together? This is the fetch-execute cycle the source talks about.
That's the one. It's the fundamental rhythm of the CPU, a sequence of steps it just repeats over and over for every single instruction in a program.
Okay, walk us through it. How does the fetch part work?
So fetch is all about getting the next instruction from memory into the CPU. It starts, remember, with the program counter, the PC. It holds the address of the next instruction. Step 1. That address in the PC gets copied into the MAR, the memory address register.
Okay, tells memory where to look.
Step 2. The memory system finds the instruction at that address and sends it back to the CPU where it lands in the MDR, the memory data register.
Instruction arrives.
Step 3. Now, this is clever. At the same time as the instruction is being fetched, the PC gets updated. It increments, usually by 1, to point to the address of the instruction after the current one, gets it ready for the next cycle.
Efficient.
Very. And step 4, the instruction that arrived in the MDR is copied into the CIR, the current instruction register. End of fetch. The CPU now has the instruction.
Okay, fetched. Now decode. What happens there?
Decode is where the control unit looks at the instructions sitting in the CIR and figures out what it actually means, what operation needs to be done.
Like, is it an ADD or a movie or something else?
Exactly. It splits the instruction into the opcode, that's the operation code, and the operand, which is the data, or the address of the data that the operation needs. Now, if the instruction needs data from memory, say, the operand is an address. The control unit takes that address, puts it in the MAR, and initiates another read from memory to get that data. That data might then be loaded into the MDR and then maybe into the accumulator, ready for the next stage.
So decode figures it out and gets any extra data needed.
Precisely. It prepares everything for the final stage.
Which is execute, where the magic happens.
That's where the instruction is actually carried out. The control unit signals the ALU, or whichever part is needed, tells it to perform the operation defined by the opcode using the data it now has ready, often in the accumulator or other registers.
And the result?
The result of that execution, it usually ends up back in a register, like the accumulator maybe overwriting what was there, or sometimes the instruction might involve writing the result back out to main memory using the MAR and MDR again.
And then?
The cycle is complete for that one instruction. The CPU immediately starts the fetch stage again, using the address that's now waiting in the program counter.
Wow. So fetch, decode, execute. Fetch, decode, execute. Just constantly.
Constantly. Millions, billions of times every second. All orchestrated by the control unit using the ALU, registers, and buses. Everything timed perfectly by that clock signal we mentioned earlier.
It really is the engine, isn't it? Running everything you see and do on a computer, from just moving the mouse to rendering complex graphics. Why is understanding this basic cycle so useful for you listening?
Well, it pulls back the curtain, doesn't it? You see how even really complex software eventually gets boiled down to these very simple, very fundamental hardware steps. It demystifies the whole process, gives you that foundational grasp of how computers actually compute.
It's fundamental.
Yeah.
So we've looked at the key players inside the CPU, the control unit, the ALU, those vital buses, and the superfast registers. And we've walked through that core fetch, decode, execute cycle.
Yeah, it's a surprisingly simple loop, but running at incredible speeds, it enables all the complexity we take for granted.
So next time your computer seems to be thinking, you can picture that cycle whirring away inside. And here's a thought to take away, building on what we discussed. We mentioned the clock signal synchronizing these cycle steps. How do you think the clock speed, measured in gigahertz, directly relates to how fast this fetch, decode, execute cycle can actually repeat? Worth mulling over.